The last lecture left off by talking about the strong nuclear force and how it's ultimately what is behind the scenes of all of the things going on with nuclear change. Um, so go back if you want to hear about the strong nuclear force, but we're going to move ahead now into looking at fission and fusion zoomed in. So, we've discussed how nuclear change is all about how atoms of one element are changing into atoms of a different element, and there's different processes for how that can happen: fission, fusion, and radioactive decay. So we will focus on fission and fusion, and the next lecture will be radioactive decay. So all of these processes, all of these nuclear changes release huge amounts of energy. And again, that's because in them, the strong nuclear force is overcome. And so when that happens, huge energy is released as the nucleus flies apart. And all of that is due to the fact that the ratio of the protons and the neutrons in the nucleus has been changed somehow. So in fission, from a big picture standpoint, it's all about atoms splitting, and fusion is all about atoms combining. So in fission, you have a large atom splitting apart to give smaller atoms, and then there's a huge energy release. And in fusion, you have smaller atoms fusing together to become a larger atom, and again, there is a large energy release. So this large energy release that occurs in either of these nuclear changes is what we think about oftentimes when we're thinking about when we hear the word nuclear. And then even beyond that, usually it's fission, which I'll go into a little bit more about why fission is more common than fusion towards the end. But when you think of things like radioactive waste or nuclear bombs or uranium and power plants and Homer Simpson, fission is behind all that stuff. So let's zoom into fission. Fission is a type of nuclear reaction, and it's initiated by a neutron. So you're going to have some changes in your number of neutrons and your ratio of protons to neutrons. Again, it's when a larger nucleus is becoming unstable somehow, and then it splits into smaller nuclei, and there's a huge energy release. A really common type of this reaction is with the fission of uranium. So let's look a little more closely about what is going on and how we can model it with a nuclear equation. So we've got these kind of 3 steps, 1, 2, 3 for each of these arrows. So in our first step, we have a neutron colliding with our uranium-235 atom with a lot of force, like that motorcycle that we just heard. So much force that it becomes a part of the nucleus. Step 2, that nucleus, you've changed the ratio of protons to neutrons, and it has now become unstable because of that. Uranium-235 is now uranium-236, and there's just too much energy at this point for it to stay together. And so the result is that the unstable nucleus ends up splitting into 2 smaller nuclei, which is barium-144 and krypton-89. The one I just realized these diagrams are a little bit different because there are different versions of this happening, but we're going to go with the barium-144 and krypton-89 because that's what we have in our equation below. So sorry, this doesn't exactly match up, but krypton 56 protons for barium. There's also 3 neutrons that get released in that process as well. which is important on the next slide. So we can always model changes to matter with equations. So we have a nuclear equation for modeling that change. Remember, we on the left have our reactants, what's going in. The arrow is the change, and then on coming out, you have the result, the products. So when we do equations for nuclear changes, we use the isotope symbols because we want to be able to really track the protons and the neutrons. So remember, on the bottom is your number of protons, and on the top you have your mass number, which is your protons plus your neutrons. One thing you want to be thinking about whenever you're looking at equations in chemistry is the law of conservation of mass, which is that mass cannot be created or destroyed. So you can track the number of protons and neutrons in each step, and it should be staying constant. Which if you pause the video, you can kind of count it. But I'm not going to walk through each of these, but it should be self-explanatory if you track the equation with what's down here. So here is your neutron that is starting off your reaction. Of course, there's no protons there. There is a neutron contributing to the mass. It is combining with your uranium-235. It becomes unstable as uranium-236, and then it continues on to split into your barium-144 and your krypton-89, with 3 neutrons getting released entirely from these nuclei. So those 3 neutrons getting released matter a lot, because what you need to remember is that atoms don't usually exist floating around by themselves. They're usually surrounded by more atoms of the same identity. So if you have like a tube of uranium atoms, when your first reaction releases those 3 neutrons, they can then start the reaction of a nearby uranium atom. And this process is what we call a nuclear chain reaction. And the nuclear chain reaction is going to release huge amounts of energy because each individual reaction releases a lot of energy, and then you have multiple reactions happening essentially simultaneously. So you have massive energy release going on. And that is ultimately the mechanism behind nuclear weapons and nuclear power. So the way that those things are different, because obviously very different effects, you can think of them as uncontrolled chain reactions and controlled chain reactions. So an uncontrolled chain reaction, like what you're seeing up here, is responsible for atomic bombs. So we've seen those twice in human history, in World War II, in Hiroshima and Nagasaki. And since then, they have not been used in wartime, in warfare. And then you have your controlled chain reaction, which ultimately it's the same mechanism. It's still fission and it's still a chain reaction, but there's more control going on. So while here it's like every atom is kind of in the path, when you have a controlled chain reaction, you're making it so there's kind of some obstacles for some of those neutrons getting released, or even access to other uranium atoms. And that is what we use in nuclear power plants. So we use the mechanism of fission to convert nuclear energy into electrical energy that we can use to power cities and stuff. The basics of what's going on are that you have fuel rods that are filled with uranium, and then again, it's controlled. But when those reactions occur, they release a lot of energy in the form of heat. And those rods are submerged in water. So, with the large release of heat, the water gets converted into steam, and then the steam can power what's called a turbine, and then the turbines spin a generator, and that ultimately produces electrical energy that can be used. And so, again, for the most part, when you think about anything with the word nuclear, what you're really most likely thinking about is the result of some fission nuclear chain reactions. Okay, so zooming back out, that was fission. Again, fission is when atoms split and there is an energy release. Now we are going to look at fusion, which is atoms combining and still getting a large energy release. So for fusion, it is also a type of a nuclear reaction. For this one, it doesn't start with a neutron or a subatomic particle. It starts with two smaller nuclei colliding, and it requires a huge amount of energy in a high energy collision in order to get those small nuclei to actually combine. Because again, you're working with the strong nuclear force, and remember, protons are going to repel each other. So there's a huge amount of energy required for that collision to actually result in the nucleus combining to form a larger nucleus. When it does happen, though, again, you get a huge energy release, even a larger energy release than in fission. And this is actually something that occurs naturally, and it's a huge part of how we came to be, because fusion is how elements are made. So, fusion occurs naturally in stars. A really common starting point is hydrogen fusing together to form helium, as you're seeing here. And hydrogens can fuse to helium. You can have smaller elements, right? They continue to kind of come together to make larger elements all the way up to iron. We've happened in stars. To get larger elements, you need even more energy. So star collisions or supernova, and also even human technology like particle accelerators. So fusion is something that occurs naturally. It happens in stars. And when you hear that pop culture phrase of we are all star stuff, that is alluding to the fact that your elements that make up your body, the atoms in your body, came from stars. Okay, so looking at how we can model what's going on in a fusion reaction, this is an example of hydrogen. So here you have hydrogen 2 colliding with hydrogen 3 under, again, high temperature and pressure in order for that to happen, which the sun or a star can provide. The high energy collision fuses together the two hydrogen isotopes, and you end up with a helium-4 atom being formed. A neutron also in this particular fusion reaction is released, and then huge amounts of energy. Again, we can model a change with an equation. Reactants on the left, arrow is your change, products on the right. Always think about your law of conservation of mass. But here, two hydrogens coming together to make a helium, and then you've got your neutron popping off. Okay, so the last thing to kind of wrap that up is to then bring that zoomed in mechanism of fission and fusion back out a little bit, and how it relates to our life and society. So remember that when we're thinking about fission and fusion in terms of technology, ultimately what it's about is the energy release, because we use that energy release for different purposes. So fission is the one that is more developed technologically right now, and so it's there's more details on it. There's a high energy release. The products are radioactive, which again, we'll jump into that next lecture. Um, an uncontrolled chain reaction is when that energy is just like all released at once. And so you have that nuclear energy converted into extreme kinetic heat, light, and sound energy that can cause massive destruction. And then controlled chain reaction is what you've got in a nuclear power plant when we're converting nuclear energy to electrical energy, which always makes me think of Homer Simpson. Fusion is there's even a higher energy release with fusion. The products are not usually radioactive. Like, for example, if you're fusing hydrogen, you've got helium as your product, and that's not a radioactive isotope, which has implications for some future technology advancement and development. Um, But there's also a lot of danger that comes along with fusion. So, because there's an even higher energy release with fusion, you can imagine the implications for nuclear weapons are significant. So, hydrogen bombs have been developed. We've never actually seen them used in war. Um, but it would be worse than the destruction caused in Hiroshima and Nagasaki. Um, so there's that. Um, that said, because you can get so much energy from very little reactants, and because the products are not radioactive, there's a lot of potential for some technology that can use fusion to have another source of clean energy that does not produce a lot of waste. But in general, there's that technology does not exist yet, and it's stuff that a lot of people are working on right now. All right, so that wraps up our lecture on fission and fusion, and next one will be radioactivity.